guys don't need to see that. Okay. So, hi everyone, I'm Julia Fisher, and I'm going to be starting off our kind of computational colloquium today with computational explorations into bilingual vowel acquisition and discrimination, model of an interesting pattern of success and failure in bilingual in two discrimination paradigms. So here's a brief overview of the talk. We're going to be first talking about what this interesting pattern that I'm referring to is, okay, how that came about. Talk about some likely factors that will, I think, contribute to that pattern. I'll give you a description of the model that I've created, kind of walk through it, and then we'll have some brief conclusions. Okay, so the first thing that you really need to get yourself started here is an understanding of the Catalan and Spanish vowel systems. They're both fairly simple systems. You see Spanish in blue and Catalan in red, and they actually are almost red and blue on that screen. So Spanish is, of course, a basic 5-vowel system, a, e, I, o, u. Catalan has 3 more vowels. It has got 2 more mid-vowels, e and a. And actually, if you see up here, MATLAB didn't like special symbols. So my e is right here, eh, and a is oh. Also, Catalan has a schwa. Okay? Now, what I want you to focus on right here are the 3 vowels a and a in Catalan and Spanish, and e in Catalan, because these are the 3 that we're going to be focusing on in this talk. They're fairly close together in form and space. Something to note. So let's talk about this pattern that we kind of noticed. This pattern was discovered using a familiarization preference procedure, which, if you're not familiar with it, is a fairly basic procedure. So you have 2 types of stimuli, A and B. Okay? What you do is you familiarize the infant to one type of stimulus, say A, for usually about 2 minutes by playing them that stimulus repeatedly. Then, during tests, they're presented with same and switch trials. So same would be presenting them with stimulus type A, switch would be with stimulus type B. And if the infants show different amounts of attention to the 2 stimulus types, then they're said to have discriminated the stimuli. Fairly basic, okay? So in 2003, Bosch and Sebastian Galles tested infant discrimination of A and E, the 2 vowels that, well, 2 of the 3 that we just saw, actually, in the template D vowel, the E. So dedi or dedi, okay? And they tested 3 different language background groups of infants, Catalan monolinguals, Spanish monolinguals, and Catalan Spanish bilinguals. And they also tested 3 different ages, 4-month-olds, 8-month-olds, and 12-month-olds. And what they found was somewhat predicting and somewhat entirely surprising. First off, all the 4-month-olds were able to discriminate the 2 types of stimuli, as predicted, because you have a non-language specific vowel space at that point in time. The Catalans, they maintained discrimination throughout development, 8 months and 12 months. The Spanish were able to discriminate at 4 months, but at 8 months they lost it, and they still had lost it at 12 months. But interestingly, you would have expected that the bilinguals would also maintain discrimination, because they were being exposed to Catalan equally as much as Spanish from birth. But they didn't. At 8 months, they lost the ability to discriminate between dedi and dedi, but at 12 months, they regained it. Now, Bosch and Sebastian Galles attributed this initially to what might appear to be a unimodal distribution. So we can check this out, okay? So what you see here is that actually the frequency of occurrence of the Spanish A is about 25%. The frequency of occurrence of the Catalan A and the Catalan E is about 9% total. And I've showed you one representation of what this could look like here, 25% for Spanish A, and I've just split the 9% evenly at 4.5% each for Catalan A and E. Doesn't necessarily have to be that. I don't actually know what the breakup is, okay? But either way, what you'd see is that you have what looks like a unimodal distribution. So what they were suspecting was that over time, you would realize that this wasn't a unimodal distribution, and you would then again regain discrimination. Well, a few years later, they tested this again. Say, okay, let's test this unimodal hypothesis using a vowel pair that actually shouldn't show this. So again, if we look at this, you'll notice that the vowels O and U are present in both languages, okay? So their distribution should never appear unimodal. But interestingly enough, again, the 8-month-old bilinguals failed to discriminate O from U, but they again regained discrimination at 12 months. Why is this happening? So they performed a couple of tests of this. So for example, they gave the infants reduced token variability. Didn't help them. They gave them a reduced stimulus form, so just de or de instead of dedi or dedi, okay? Didn't help them at all. Then they said, well, can they discriminate anything? So they tested them on A versus U, and they succeeded at 8 months. So what really seemed like was happening was that they were having trouble with certain close contrasts in formant space. They hypothesized that this might have something to do with the large number of Spanish Catalan cognates, which we'll come back to. Okay, now 2 years after that, they did this same test again, except with a different paradigm, an anticipatory eye movement paradigm. It's also fairly simple. You have two types of stimuli, A and B. Infants are presented with this T-shaped kind of black box, and unfortunately you see the little cartoon character, smiley face at the bottom is halfway off the screen there. But what happens is that you associate essentially one type of stimulus with the left side of the box and the other type with the right side. So this cartoon character flashes, and then it disappears behind the box and it appears on one side. And as it's doing that, that left side stimulus plays. So you'd hear dedi, dedi, dedi. Then, again, the cartoon character would disappear behind the box, and the infant would hear dedi, dedi, dedi. So what the infant would be learning in this paradigm is how to map a certain stimulus to a certain side of the box. Okay? Now, interestingly, in this paradigm, the Spanish-Catalan bilinguals succeeded at 8 months. They could discriminate these two types of stimuli. Spanish monolinguals could not. Okay? So clearly they were able to discriminate A from E, but at the same time, they weren't able to discriminate A from E, which is a kind of interesting situation to find yourself in. When they're not presented with really attention-grabbing information, they fail. When they're really given referent information, left, right, there we go, they succeed. So one thing that's worthwhile thinking about at this point is what could be influencing this pattern, okay? And I think there's probably a lot of things. Certainly word-level influence on phonemic development, number and types of cognates, and done that all day. Catalan and Spanish, not Kaddish and Spatalan. Yes, I've been saying that all day. Also distribution of phonemes in formant space, frequency of occurrence, and then variation in the input, which is pretty high for these infants. So phoneme selection errors in their parents and caretakers, dialectal variation, and percentage of each language heard. And then, of course, there's other language-specific factors like prosody and so forth. The model that I created focuses on these first two factors, influence of word learning on phonemic development and presence of cognates. So we're going to just talk about those very briefly, okay? So the first thing you might be asking yourself is, Julia, if you're supposing that word learning can influence phoneme acquisition, you're supposing that 6-month-olds can learn words, which is a pretty big supposition. But there is evidence to support that. So for example, Jusic and Hone in 1997 presented infants with a series of stories over 2 weeks. And then they tested them on their preference for words heard in those stories to words not heard in the stories. They highly preferred the words heard in the stories, indicating that not only were they storing those words, but they were storing them in an abstract enough form that they were able to associate a list form speech from the lab with a more connected form of speech. Okay? Similarly, 9-month-olds were tested by Paris and Sibra in an congruous and incongruous picture object naming task. Okay, so this was an EEG task. You'd have the infants in the EEG system, and you'd have a parent next to them or an experimenter. And the parent or experimenter would say, you know, look at the duck, here's the duck. And then a picture of a duck or something that was not a duck would appear on screen. They measured the infants' N400s, okay, so a measure of semantic incongruity or semantic processing in general, and found that when what the parent or the experimenter, actually this only held for the parents, not for the experimenters, but what the parent was saying did not match the picture that they were seeing, then there was a spike in their N400, okay? So A, they're engaged in some form of semantic processing, and not only that, but they are able to figure out that what they had heard didn't match what they were seeing, so they had some sense of meaning. Now, you can even go as young as 6 months here. Bergelson and Swingley in 2012 showed infants pictures with kind of critical items and non-critical items, or scenes, and found that if you were to name the critical items in a sentence, they looked a lot more at the critical items than the non-critical items. They have some sense of meaning by 6 months. Okay, so establishing that, why do we think word learning may influence phoneme acquisition? Well, I think there's good reason for that too. For example, Thiessen in 2007 showed that 15-month-olds were able to discriminate between da and ta if they were presented with da and ta in genuinely different contexts, non-minimal pair contexts. Okay? If instead they were presented with da and ta in minimal pair contexts, so the examples I'm giving here are dagu and tagu, as opposed to dago and tagu. So if they were given minimal pair context, they had a lot of trouble discriminating between those two phonemes. Okay? So what we see here is that minimal pairs can actually hurt your ability to discriminate if you're not given referent information. And again, this was shown with adults by Feldman et al. In 2011 in an artificial learning paradigm. So what we see here is that if you supposed you had a lexically based phoneme acquisition system, and you had a lot of minimal pairs without good referent information, then you would expect there to be some problems with discrimination in that system at some point. And in fact, this is what we have in Catalan and Spanish. These bilinguals are being exposed to a lot of cognates, okay? And these cognates primarily differ, according to Sebastian Gallés and Basque, in fricatives or in vowels. And if you look through the list, those vowels are often an OU difference or an A difference, A in Spanish and Catalan, okay? So for example, you would see pairs like patu or pato, Spanish on the right and Catalan on the left, meaning duck, tren or tren, and café or café, okay? So they're very similar, these cognates. And, you know, this isn't really just limited to high-level words. What you can see here is that these are fairly basic words. In fact, if you look at the MacArthur-Bates Communicative Development Inventory, a lot of the words that infants should know by, 1 to 2 years are cognates, okay? So this is the system that I proposed. We have a lexically based system. You're learning words. Through word learning, you develop phonemes. And in that process, having a lot of cognates where essentially they're minimal pairs because they have the same meaning, you get this interesting pattern of development. So let's talk about the model briefly. Oh, it's kind of off the screen, but that's okay. So basic model structure. First step in the model is to acquire words, okay? And when you acquire a word, it comes in with a lot of different information. It comes in with consonant information. I'm assuming the model knows consonants since I'm mainly focused on vowels. It comes in with first and second formant information for vowels. And it comes in with some referent information, okay? Things that this word could possibly mean. So the first step in the model is to parse the word into what I call a consonant frame. Essentially, that's just taking out the vowels and putting placeholders in. So if I were to say the word cat, the consonant frame associated with that would be k, t, k space t. You can see that right here, okay? Then the next step is to figure out what are my formant values associated with that vowel. What I've done here in this model is actually bin the formant space for kind of ease of computation. I think a future version of the model might not deal with a bin space, but I've done that for right now. And so you say, okay, well, what's my formant values? Which bin does this fall into? Okay, you mark a hit in that bin. And what you'll notice here, do I have a mouse? I don't have a mouse. Okay. What you'll notice here is that some of these bins in this example have been hit. You'll see little dots there, okay? Now, associated with each of these bins, we have a referent distribution. You can see some of these here: wound, dog, cat, cup, and so forth, okay? And since you came in with some referent information, you take that referent information, you look at the current histogram for that bin that you came in on. Say we hit this bin right here, okay? And you add that referent information to the current bin. So essentially, every bin in this space gets associated with a distribution of possible meanings, and then it has some hits to that bin. You keep track of how many times it was hit, okay? So you do this a lot. I usually feed the model about 1,000 words at once. Now your next step is to attempt word recognition, okay? So first thing in word recognition is you need to acquire the word, because if you haven't heard it before, you need to have a consonant frame in which to work computationally, okay? And then given the formant bin of that word's vowel, you calculate two measures of connectivity. So let's think about the first one here. Local connectivity. Essentially what you're doing in this, and you're saying, okay, I hit this particular bin right here. Well, given that, what's the probability that I could have hit any of the other bins in this formant space? Now you calculate that information given the referent information between the given bin and all the other bins, and given the hit information, okay? So it's just a probability. The global connectivity is very similar, but the local connectivity only takes into account the current consonant frame. The global one takes into account all the consonant frames you've heard. So it essentially says, well, what are all my different probabilities? Let's combine them together into a single probability, okay? So you've got local and global information coming into play here. And what you do is you take those two measures of information and you use them 5 minutes, yes, thank you. You use them to actually create a weighted referent distribution for that word that you just heard. Now, given that weighted referent distribution, I know I'm glossing over stuff here. Given that, you say, well, do I have a referent that has a high enough probability? Now, high enough could mean different things. For my current model, I'm taking it to mean 75%. You want to be pretty sure that that's what you meant when you heard that word, but it could be different, okay? And if it's high enough, then you say you recognize the word. If not, then you didn't recognize it. You go through this process quite a bit. Actually, this process is used to help toggle one piece of the model and help it automatically adjust itself a little, okay? So you go back there. Now, after you have attempted recognition, you perform 2 tests of the model because we want to show that it can actually perform in this kind of familiarization preference procedure and this anticipatory eye movement procedure. So here's how we test the anticipatory eye movement procedure. Okay? Token variability and whatnot, number of trials are all the same as in the actual test. And in each trial, what the model does is it attempts to recognize the word, and it's considered correctly anticipated if the probability of the correct side of the T, okay, is greater than the probability of the incorrect side. So what you do is then you look at 2 halves of the stimuli. You present it with a ton of stimuli. And is your percent of correctly anticipated trials greater in the second half than in the first, indicating that you've learned? If so, then we say it succeeded at this discrimination. If not, it did not. The familiarization preference procedure is similar. The word comes in, the infant tries to recognize it. If it fails, and it should fail because no clear referent information is being given in this procedure, since the words don't actually refer to anything, then what it does is it says, well, I don't know what this means, but is it similar to anything else that I've heard? And it tries to group words. If, during the same and switch test trials, it groups the same trials into a single group and the test trials into a different single group, then we say that it has discriminated the stimuli. After this, we undergo a process of forgetting, since the model is not perfect, humans are not perfect. And this involves forgetting both hits and referent information associated with those hits. Okay? That's the model. Now let's just walk through it a little bit. I am still having some issues in getting it to work a little bit, so I can't present actual results right here. But I can talk about why I think this model should produce the patterns that we described in the beginning. Okay? So it goes through a couple of stages. First stage of the model, when you're initially presenting it with information, the model should be highly variable. It doesn't have enough information to settle on referent information or phonemes. So we don't care about that stage. Stage 2 is where stuff starts to get really interesting. So in stage 2, you've acquired just enough information to begin to start seeing phonemes. And phonemes in this model are areas of higher probability. Okay? So you have kind of high probability clusters. But you don't expect that you've really got fully formed phonemes yet. In fact, what is likely to happen is you've got little clusters, where if you had a single phoneme, you'd maybe have 3 clusters instead of 1. Okay? So we'd expect here that you'd have more phonemes than you should, and they should be covering smaller areas. Okay? So if you think about the familiarization preference and anticipatory eye movement procedures here, we should succeed because if you have lots of small clusters of things, you're going to succeed in discriminating pretty much everything, okay, whether or not you have referent information. Now the next stage is probably the most interesting stage. At this point, you should have acquired enough information that you've mostly got your phonemes down, but not quite. Since you have so many cognates that involve A and F, for example, you should expect to see a continuum between A and F of probability mass, okay, with higher probability at the 2 A centers and at the S center, but still a fair amount of probability in between them. So in this situation, you would expect familiarization preference to fail because you've actually only got global information to go on here in this procedure. You have no local referent information to tell you what's happening. And your global information is telling you that these things are all highly connected, okay? So you shouldn't succeed. In contrast, in the anticipatory eye movement procedure, you get very strong local referent information. You're told that Dedi is this side and Dedi is this side. So if that's the case, even though you've got global information, which is telling you to combine these things, your local information is telling you to tease it apart. Okay? So we would expect that they would still actually succeed in the anticipatory eye movement paradigm. And the last stage of the model, you would expect it to succeed because at this point, you would have had enough information, enough input to the model that yes, you would always have a continuum between the A's and the E, but that continuum would be lessened. You would get more probability mass moving to the particular A's and the E. I'm out of time. Okay? Yes, it quacks at me. Okay? You would have more probability mass at the actual phonemes themselves and still a continuum, but less in between. And so with that less information in between, again, you should be able to discriminate in both tasks. Okay? And to conclude, in general, we saw that there was an interesting pattern with Spanish-Catalan bilinguals where they were both able and unable to distinguish between certain close vowel contrasts at 8 months. Okay? And we hypothesized that it was a large number of cognates in their inputs combined with a lexically driven phoneme acquisition system, which could account for this. So that's the model I'm proposing. And this model accounts for this pattern by deriving formant space connection information from both referent and hit information, and then allows both global and local information to play a role. And here are my references. And thank you goes out to many people, including my committee members, Cobus Barnard, Thomas Bever, Luann Gurkin, and Andrew Wadle, who is not here either. My prelim class, who is also fantastic, Diane Arcangeli, Dane Bell, Rolando Cotosano, and Jorge Muriel. And then also to Miguel Simone for his help and Antonio Rubio. So thank you.